Homework questions from anybody? Dawn? Number 3? Sure thing. Ooh, God bless you.
That was a big one.
All right. So here it's telling us to do f of 1/3. And there's nothing to really simplify here exactly. So at this point, I'm just going to type that into my calculator, because I know 1/3 power is the same as a cube root. Or I could just type it in my calculator as like a 1/3 power. No, because 1 cubed isn't 3. 1 cubed is 1. Right, the cube root of 3 is like 1.69 or something. Oh, 144. So if I take like 1.44 and I multiply it to itself 3 times, stop talking please, I get just about 3. So does that feel okay? So that's negative 288 there or whatever. I'll do this. I rounded some squiggles. I think Dubrovnik is the capital of Croatia also. Boom. What? Oh, is it Zagreb?
I'm not sure.
It's a city in Croatia, I think, Dubrovnik. It's Eastern European. What else? Other homework questions? Anybody got them?
6.
6?
Yep.
Sure. It's the 7's the scariest number.
Right.
Do you know why?
7.
Yup. All right. So 6 asks us to write the formula for g of x using the table. What I'm going to be using, I could use any of these values from the table. I'm really going to be using 0 and 1, and since I'm doing g of x, I'm looking at that. So what that tells me is that since it's exponential, g of x is 12 equals a times b to the 0. B to the 0 is just 1, so a is 12. And if I use the next point, I can say 4 is equal to a, but I know that's really 12, times b to the first is equal to 4. And then if I divide both sides by 12, I get that b is 1/3. So putting them together, I got that. It's okay, man. It happens. Dwan? Yeah, I'm going to do the exact same idea, but I'm going to just, because this one's f of x, but I'm going to use the same x's. So again, f of x says it's exponential. So I'm going to start with the 0. So I have 3 over 2, that's f of x, is equal to a times b to the 0. So a is just 3 over 2. Then I'll use the other point. I have 3 over 4 is equal to a, which I know now is 3 over 2 times b to the first. So to get the 3 over 2 out of there, I'll just multiply by the reciprocal, which is 2/3. So I have b is 1/2. Yep. So I just say f of x is equal to 3 over 2 times 1/2 to the x. Who's next? Boyd. 15? Sure. Okay, this says the population P in millions of people of Ohio, T years after 1900 can be modeled by the equation P of T equals yada, yada, yada. Based on the above equation, when was the population of Ohio 10 million? So since it's a when question, I'm looking for T, right? So I'm going to take P of T and set it equal to 10 million. And then I'm going to solve for T. Now, algebraically, we don't know how to do this yet, but the calculator can handle this for us. Just a question of getting it into our calculator correctly. So I'm going to just start by typing this equation into y1. Now I'm going to use the fraction command. Boyd, I don't think your calculator has that. So if it doesn't, yeah, make sure you put that all of the denominator in a parenthesis. And I think you'd probably have to put another parenthesis around all this exponent to get it to come out the right way. The advantage of having the calculator with the new operating system is that it does the math print for you so you can see exactly what you're typing in. Henry, what's up?
How would you put the T in
Well, I'm just using an X in place, right? Just the name of the variable doesn't really matter. So the calculator uses X's, so I'm just going to replace the T's with X's.
But isn't E and T the two?
E is a number. E is a constant.
Oh, it's just the...
Right, it's that Euler's number that we talked about the other day in class, like that, whatever, I forget the decimal for it, 2 point something or another. And then I'm going to do 10 million, so 10 and then 1, 2, 3, 1, 2, 3. And then I'm going to set a window. So I don't know what the current population of Ohio is, but I imagine by the year 2000 we've gotten to 10 million people. So we're starting at 1900 is what it says. So I'll just go 100 years. And then the minimum sure can be 0, and the max, I just want to pick something bigger than 10 million. Yeah, Boyd?
So for Y2, do we plug in 10 million?
Yes. Yes. So I'll do 15 million as my other one. So the 10 is just like easy to see. So 15 and then 1, 2, 3, 1, 2, 3. And then we'll go up by millions. So 1, 2, 3, 1, 2, 3. Let's hit graph. So there's my 10 million line. Uh-oh. Oh! Read the question, Mr. Kulik. It says P in millions of people.
So we just plug in 10.
Yeah. So that should just be 10. And then obviously I have to adjust the window as well, since that was all cuckoo crazy. There we go.
Yeah.
That feels better. There's a nice intersection. Easy to see, so second trace. Choose the intersect command. Enter, enter, enter. And I got 69.67. So I would say that this occurred during the year 1969.
So, does that look right in the calculator? Oh wait, I have 100. It's supposed to be 10. That's probably why, right?
Okay. So you have, no, there's an issue here. So this should be E, not X.
Oh,
So I'm going to do the E, and then here, I need an X.
oh, okay.
And then if we hit graph,
I got it.
there you go. That looks like it's doing what it's supposed to. So again, like, notice what we did here in terms of me writing stuff down. Very little, right? The calculator did most of the heavy lifting for us right now. So again, when you get to these, really important, you're able to get this stuff in your calculator correctly and consistently and be able to use your calculator to kind of get the answers to spit out. It's not difficult to do, but like, might take a little bit of practice if you don't feel very calculator confident. And if you need help with that, please speak up and come see me. Boyd's been to see me a bunch of times because he has the calculator with the old operating system that doesn't do like the math print on it, which makes it a little bit harder to get the stuff in. Which is fine. It still works. His calculator does everything it needs to, but it's just not as user-friendly as some of the newer generation ones. Last call on questions. Dwan? 8, you said? Okay. So, same idea as the previous ones, but it's a little bit more difficult because you're not given convenient x's, right? So, what I would start by doing, again, we're looking to build an exponential equation. So what I'll end up doing, since neither of the x's are 0, I'm using these ones, I guess, I have to set up a system. So I'll say 16 over 9 is equal to a times b to the second. And then 32 over 27 equals a times b to the third. And that's going to really be my system. So to solve this system, because the variables are being multiplied together, instead of adding and subtracting these two equations to do elimination, I'm going to be dividing. So what I do is I look at the exponent, and the equation with the bigger exponent on the variable is going to be the numerator of my division problem. And the one with the smaller exponent will be the denominator. So when I multiply or divide the left-hand sides of b and a, I'd have 32 over 27 divided by 16 over 9. And I'd have a times b to the third divided by a times b to the second. So the right-hand side, I notice, okay, well, I can reduce the a's and reduce the b's. And then to do that numeric piece, I know that dividing fractions is the same thing as multiplying by the reciprocal. So 16 goes into 32 2 times, 9 goes into 27 3 times. So I'm left with that b is equal to 2/3. Then from there, I'm going to plug that into one of the two equations to solve for a. I'm going to choose to use equation a because the exponent on b is smaller there. It's just going to make life a little bit more convenient. Two-thirds squared is 4/9. And if I divide both sides by 9 over 4, or I'm sorry, by 4/9, that's the same thing as multiplying by 9 over 4. And there again, I can reduce and just get that a is equal to 4. So I'd say here k of x then is 4 times 2/3 to the x. Okay. Yeah, Boyd?
Also go over 6.
Yeah, sure. I suppose we're not in that big of a rush. Okay. The population P in millions of people, remember that, Mr. Kulik. Don't make the same mistake. Of New York State, T years after 1800 can be modeled by the equation P of T equals yada, yada, yada. What was the population of New York in 1850? So T is the years after 1800. So the T here should be 50. So I just need to do P of 50. I'll do that in my calculator in a moment. Part B says, okay, what will the population be in 2010? So the T there should be 210. And again, I'll do that in just a second. And then part C asks, what is New York's maximum sustainable population? Well, I notice since this is a negative in my exponential, that this is a growth. So my maximum is just going to be y equals c. And the c in this case is 19.875 million people. Okay, let's go back and get those other values that we actually had to use the calculator to get. I am going to, rather than typing these in, I'm going to just type in the function into my calculator and then have it insert those values. Since I have to do it more than once, it's probably easier than trying to type it into the main screen of my calculator, although you could do it that way. There's nothing wrong with doing it that way. Okay, so got that in to y1. I'll do vars, y vars function, y1 of 50. So that's 1.79 million. And then if I do the same thing, I'll just press second and enter to recall the same thing, go back and edit. In 2010, we're at 19.16 million. Ooh, we're getting pretty close to that maximum sustainable population. Maybe our model is wrong.
So how did you know that the 19.875 that was in trillions?
In millions?
Oh, I thought it said
That's supposed to be an M.
okay. Yeah, that makes sense.
Okay. Trillions does not. Be a lot of people. Yeah, it's only like, 1,000 times the global population can live in New York State. What? That'd be a lot of people. Be a lot of people. All right. You ready to get the show on the road, folks? Okay. Okay.
It hasn't synced since the 17th.
Okay. That's a problem.
Yeah, and it's just this notebook.
Hmm.
Fucking 6 for T.
Okay. So let's talk about specifically doing some modeling problems using exponential and logistic functions. So last time we talked about exponential and logistic functions, and we kind of used them to create our models, or based our models off of these things here. We're going to be like building the model ourselves and then doing stuff with it. So we'll start by just talking about the exponential population model. So if the population P is changing at a constant percentage rate R for every T units of time, whether that's days or months or years, then the exponential model can be given by the equation P of t equals P naught times 1 plus R over 100 to the T, where P naught is the initial population, R is the percentage rate of change written as it's just the percentage rate of change, and T is time. Notice that this is still just an exponential equation in the form A times B to the X, right? Where the A is the P naught and 1 plus R over 100 is the B. Can we all see that? So the same rules about growth and decay hold. So let's take a look at a couple of these. Oh boy, that was bigger than I wanted it to be, whatever. So let's take a look at these two population models. And we're first going to ask, are these growth or decay? So looking at part A, is that growth or decay, and how do we know?
Grow, because it's above 1, the p-value.
Excellent. So we'd say that this is growth. B, which is equal to this, is greater than 1. What is part B?
Decay.
Great. So that's decay, because the B value, which is 0.8 or 0.98 change, is less than 1. Great. Now we also ask for something else, right? We ask you to find that rate, that constant rate of growth or decay. So how do I do that? Well, I'm going to take my value for B, and I'm going to set it equal to 1 plus R over 100. And then I'm just going to solve this equation then for R. So the first thing I'll do is subtract 1 from both sides. And then I'll multiply both sides by 100. So I have R equals 3.84%. We'll do the same thing over here, What should we be expecting with our R? Since this is decay, expect the R to be negative, yeah. So I'll subtract 1 from both sides. And then multiply both sides by 100. And there we go. Did you get it?
Yeah, it wasn't showing up anything.
Okay. Let's do another example using this model. So this time we're going to give you the situation and ask you to write your own model. So it says, determine the population model. So I know we're writing something like that because it says population model with an initial value of 15. So that's P of naught or P naught, and a constant rate of 6%. That tells me R is equal to 6. And then every year. So there's that. If I do 1 plus 6 over 100, that gives me 1.06. And that'll do. Maybe we should make mention that T is in years here, but you don't really need that since it makes it clear in the problem, but everybody okay with that? Just kind of plug in the stuff into the formula, right? You just have to go from the words to the symbols. You know what I mean? But that's not too hard. Pretty doable. Let's do one more example kind of like this. Okay, it says determine the population model. So I know that we're going to be writing one of these. Has initial value of 15. So P naught is 15. Constant rate of 6%. So R is 6. But here it says every 6 months. That's the only difference.
Could you do that as 1/2 if you're in years then? Would that be possible?
Yeah, so we're going to write this much, right? And if we do T in years, how many times does 6 months happen in a year?
Twice.
Twice. So we'd say 2T. If we had written this in months, that would be the other obvious option.
Yeah.
How many times does 6 months occur in 1 month?
6.
Well, 1/6, right? So this would just be like T over 6. Because there's 1/6 of a 6 month period in a month,
Yeah.
right? So either answer would be okay. So again, this would just simplify down to like 15, 1.06 to the 2t, or 15, 1.06 to the t over 6. Yeah, and depending on like what you're going to use your model for, you would pick whether you want to do it in years or months, because whatever the data you were going to model from it, if you needed yearly data or monthly data, that's fine. So we're stopping here. Go to lunch. We'll see you guys. Next example. So we've seen if the time isn't like a standard unit, what to do. Now what we're going to do is look for what if the R value is hidden.
Ooh.
So again, suppose that a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. How long would it take there to be 400,000 bacteria? So again, clearly this is a population situation, right? Okay. So what is the 120?
PO.
That's our P naught. Yep.
What's that called?
P naught.
Alright.
The 0 is like a knot. Okay. That looks good to me. And what is our R?
Would it be doubles every 3 hours of doubles?
Okay, doubles. What does that mean for R? It's a percentage, right? R is a percentage,
200%.
not 200. So if you have 2 and you get 100% more, it goes up to 4, right? It doubles. It's the same thing. Did you say up? Oh boy. Okay. And then we need to decide what time unit we want T to be in. T is in hours?
Yeah.
Okay, so what should the exponent be then?
3.
Not 3.
Oh, 3.
Needs to have a T in it for 1.
Would be 3.
It's not going to be 3T because 3 hours doesn't occur 3 times in 1 hour.
That's actually choosing 1/3.
There you go. Or I'll just write T over 3. Yep.
What is quadrifusive?
Okay. So that's that. And again, we could simplify that down now. So 100 over 100 is,
1.
and 1 plus 1 is,
2.
there's your doubles, right? That's not bad. Oh, and then we have this second question, though. Predict how long it will take for there to be 400,000 bacteria. So how are we going to solve for T here?
I say we just toss in the shot.
Yes, sir. Hey, nobody's stupid here.
No, I scooping.
Stupid?
No, I didn't. He has a tub of aquaphor and goes. He gets it in his nails. Some aqua.
What?
Let's focus.
What does it matter how much aquaphor he has? It's just like some lotion or whatever.
Actually, put it on all my food.
On your food?
Yeah, it's good for the soul.
The sole. I think it's good for the soles of your feet, probably.
I am so smart. I'm using you. Bombastic.
That's enough.
Okay, that's enough.
Yeah.
I'm drawing the line.
Did you really?
Bombastic. I don't know that. You don't know bombastic? Can you tell me the definition of
What is
bombastic?
boobas?
Oh, why are we all pronouncing
Bombastic.
it differently? It's bombastic.
It's
Oh.
like
Just
a
huge,
Extreme is bombastic.
Bombastic.
You know what, guys? Look at what I did. How dumb is this?
You're not Mr. Cool. Like,
Right.
Nobody here is stupid.
I wrote.
Oh, wow.
I underlined the 120 and then I wrote 15.
That's okay.
How did I do that though?
Mr.
You know, I have no idea.
You know, like,
You're dumb and one alive.
I mean, like, here's the thing. You have the excuse of like, this is the first time you're doing it. This is like the 30th time I'm doing it.
I still think after the 30th time, I want to be math.
Yeah.
The math is not math.
Well, it's nothing to do with something.
There we go. 3511 sounds good.
Is there like one subject in Mr. Cool that you're not good at?
I am a terrible artist.
Okay.
I feel like that's not even true.
I
I feel like you say that and then you just count.
Core
No.
subject.
I feel like you'd like whip out like a exact duplicate of your starting night when you hear that.
No.
Core subject that you know, like, you're really good at.
Nothing.
No,
Imagine walking around like this.
I don't know. Like,
Are you strong in history?
I'm gonna look.
I know a lot of history.
Who was the 32nd president?
Who cares?
I bet there only been.
Got him. Dumb.
No.
How many?
Oh,
40.
46. I'll figure it out. Okay, get it.
Oh, it's gonna.
Oh, well.
30 seconds.
Oh,
Okay,
okay,
no, I
okay.
can't do it.
30 seconds was
Right.
O'Brien.
We're playing.
You gotta go back way further than
Way
that.
further.
Uh,
Probably.
Madison.
Those are on Roosevelt.
I'm gonna go with Cleveland because he was president twice.
And they weren't the same.
Yeah,
Oh,
so
no,
that's
it's
your biggest
not.
probability.
I have no idea.
It's not.
Grover Cleveland?
Cleveland
You
Brown.
don't know who Glover Cleveland?
I know,
Awesome,
I know.
dude. Is it Calvin College?
No.
I said it.
Federal.
Oh, wait. 30 seconds.
Franklin.
Ooh.
Franklin.
Franklin Roosevelt.
Where did you whip out federal officers?
Did you watch the show?
All right.
I called it Roosevelt.
Roosevelt. That would have been a good one too. He was, I think he got elected 4 times.
Roosevelt.
Yep.
Yeah.
The
FDR. Yeah, he's great.
I learned
World War
that.
II.
I learned that in U.S. history with the
Oh,
I didn't get all of them.
Nice.
All right. Simmer down here, folks.
It's a Friday. It's good.
I know. I get it.
What's the island now?
All right. We have one more model to talk about. That's the radioactive decay model. So, do you guys know what radioactive decay is?
I don't know what radioactive is.
I do. I'm a big fan.
Spider-Man.
So, you have in chemistry, certain isotopes are unstable. We call those isotopes radioactive. So, common radioactive isotopes would be like carbon-13 or uranium-238, or no, plutonium-238, or whatever, like there's a bunch of them.
Yeah.
Basically, any element can have a radioactive isotope. You just need to bombard it with enough. Anyways, it's not important. The rate. So what happens is they're unstable, so they're going to eject nuclei to fall to a more stable state, right? That nuclei that it's ejecting is the radiation. So over some amount of time, that nuclei randomly ejects. The amount of time that it takes for like a sample, for half of it to emit that radiation and turn into a more stable substance is called the half-life. That's the gist of it. But basically, this is just a population model where the growth rate is always, or the R is always 1/2. So that's all the dealio is. So we're just going to think about this still as our population model. You know, half-life R is negative 50%. Because it's decay, that's why it's negative. And half is why it's 50%. So if the length of the half-life is 35 days, that means that if I measure t in days, my exponent should be t over 35. And we start with 10 grams, so that's like my P naught. And then this is what my P of t will be that I'm solving for. So if I go ahead and I just kind of plug this in, and then I simplify down, there's my model. And the last part of it says find the time for there to be 1 gram remaining. So I'm just going to solve P of t then equal to 1. And again, we're just calculatoring this. But it's basically the same thing all over again, right? NBD. Oops. Okay, I'll do that. 0 to 100 sounds fine. This should be 0 to 10. And, oops, to 10. Goodness gracious. Okay. So there's my exponential decay. Here's the line y equals 1. Oh no! What do you notice? It doesn't intersect it yet.
For now.
Well, I just make that window bigger. I'll go to 200. I'll show you. There we go. Now it crosses. Hey! Second trace, intersect, enter, enter, enter. And I got 116.3. And what is the unit here? Days. Because we decided to write this in days. Pretty easy, right? Same old, same old.
So it's like a variation of the...
It's just another application of the population model. It just, the thing you have to remember is half-life means that R is negative 50.
All right.
That's all. Very, very easy, right? Like nothing special about it. Nothing complicated. This doing the same thing. This is my last example. Can we kind of pull it back together here, Gossip Corner? For just like 5 more minutes to finish this out. Thank you. It's okay, man. You start a bunny petting zoo. You determine the population of bunnies on your farm can be modeled by the equation B of t equals yada, 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 where t is measured in years. How many bunnies do you have initially? What time is initially?
Usually is the start.
Initially means time is equal to? What do you think?
0.
0, yeah. So we just want to do B of 0. We'll do that in our calculator in a minute. Part B is the maximum sustainable population. So again, I noticed that because the exponent of my E is negative, I know this is growth. So the maximum is going to just be y equals c. And the c in this case is 800. Oop. And I guess those are bunnies. Cute little bunnies. And then it says, how long will it take to get 500 bunnies? Well, I'm going to use that to solve for t. So set b of t equal to 500. Use my calculator to get my value for t. All right, well, let's plug this model in and start grinding this out. Get our grindage on. So I'm just going to go ahead and plug in the formula. Notice that I'm using the fraction command on my calculator because that's ever so helpful. Do 500 there. Exit out of here. First thing I'm going to do is that b of 0 that we set in the beginning. So I'll do that vars function y1. So that's 8 bunnies. We started with 8 bunnies, huh?
8 bunnies?
And let's figure out how long it's going to take us to get to 500. So here we got to go back and reset our window. I'm guessing I'm not going to need 200 years there. Bunnies kind of are renowned for their ability to reproduce quickly. So I know the maximum's 800, so let's do that and go by 50s or something. Okay, that looks good. Fire that off. There's my nice S-curve. Here's 500. There's my intersection. Second trace, intersect command, enter, enter, enter. 10.2. So in 10.2 years, I've turned my 8 bunnies into 500 bunnies. Those bunnies were getting busy. And that feels good for today. So at this point, you guys should be able to do up through 36. Is that due Sunday?
No.
No. When would it be due? Next Sunday. That sounds great, like the 30th or whatever. What's due this Sunday?
1 through 16.
Just 1 through 16. You got it, dude. Somebody's been paying attention. I love it. All right, I'm out.